But here we consider that angular momentum to be 0. Then why these dipoles are further deviating? Like if, for example, it is having no orbital angular momentum, it should strike exactly here at the center. But when it moved through the non-uniform magnetic field, it experienced some force, and that force moved it. Because it's a dot product, it will get some direction here. And it moved here and here. 2 spots were there. And from here we know that the angular momentum, the integer we know, that 0, 1, 2, 3 we know. So we know 1 and 2 and this, but we don't know from where this 1 or 2 is coming. Like 0, 0, 1, then and half, and then 1, and then 1 and 1/2. So what it will be? 3 over 2, and then 3, and so on. So the half integer values from where they are coming in, and this shows that there are 2 possible ways. If we give a property like a classical spin to this electron, then this electron will have 2 values of angular momentum, spin angular momentum. One will be plus and the other will be minus. So the very first value which is coming in is half here. This integer we know. The half integer values, the very first one is coming is plus half and minus half. So if this one is plus half, this one should be minus half. And then the next will be coming is 3/2. Clear? So we give that this spin, which was just like a classical spin, it is not dependent on the theta and phi. You remember the angular momentum was dependent on theta and phi, but this spin is not dependent on them. We are not solving it from the Schrodinger wave equation, and we say that unlike the classical spin, this is the intrinsic property of the elementary particles, intrinsic spin. If I consider Earth is spinning, so it means the dirt of it and the sand and all the ingredients of it are actually spinning. Right? So that I understand, because our Earth is having some structure, it is having some ingredients. When I come to the electron, it is structureless. So it is not physically spinning like our Earth, but it is having spin angular momentum. And the reason for that I don't know. That's why I will have to put it in the as the intrinsic property of this elementary particle. You know the 2 properties already of the body. One is the mass of this electron, from where the mass is coming in of an elementary particle. We don't know this in full, from where mass is coming. Only the 2010 Nobel Prize, you know about the Higgs boson or the Higgs field. The Higgs field, Peter Higgs was awarded Nobel Prize for this thing, where he explained some portion of this thing that from where the mass is coming in. It is coming in the Higgs field, but yet the search is going on. And we are not fully clear about mass. Though media started calling the Higgs boson is the God particle. They God created first this one and it started giving mass to the bodies. But Peter Higgs said that no, it's not a God particle. God would have created maybe something else. This is one picture of it, that where it is getting mass. So we put mass in the intrinsic property. And the other is charge. Charge of electron is also its intrinsic property. We don't know the reasons behind this one. It is an intrinsic property. And the third property of the particle we are putting in is the spin. Spin is an intrinsic property of the elementary particle. There are some particles whose spin is 1/2, 3/2, and 5/2, and so on. We call them fermions. Fermions like electron and proton, they are spin half particles. We are having bosons. They are spin 0 particles. Like photon. Photon is a spin 0 particle. And all other elementary particles are having their spins. So, spin we will also put in the intrinsic list, that it is an intrinsic property of the material. Clear? You got the idea of spin. That it is an intrinsic property. When we come to the electron, it's a structureless particle, so we don't know, or we know that it is physically not spinning, because physically something will be spinning. When it is having no structure, then physically it is not spinning, but it is having spin angular momentum. As this is angular momentum like L, then all the properties we studied for the L will be applied on the spin as well. For example, we studied that some commutation relations Lx Ly is IH bar Lz. This commutation relation we studied. We derived it properly from the Schrödinger wave equation solution. Right? Yes? Anyone want to say something? Okay. So,
spin हम इलेक्ट्रॉन के बारे में कहेंगे स्ट्रक्चर वैसे हम प्रोटॉन और इंटरनल स्ट्रक्चर है उसमें ये स्पिन इंट्रिंसिक प्रॉपर्टी होगा सर
उसमें भी intrinsic है. This is also an intrinsic property for the proton as well. But we observe this for the electron here in the Stern-Gerlach experiment. Because we are not measuring the spin of the proton, we are measuring the spin of the electron here, the spin angular momentum. This deviation is the angular momentum. You know, linear motion is linear momentum. Curved motion, angular momentum. This is a curved motion. It isn't struck here, but there is a tangent. So angular momentum is there. And this angular momentum we consider to be 0 due to the orbital angular momentum. But yet there is some angular momentum, and that angular momentum we attribute to the intrinsic spin of the elementary particle, which is electron in this case. Right? So here, this we have proved already, and now the same will be true for, if I represent this orbital angular momentum, then this is spin angular momentum Sx, Sy, and this will be equal to IH bar SZ. It is also in angular momentum. So it will also follow the same procedure, and similarly SY and SZ will be IH bar SX, and SZ with SX will be cyclic permutation of this thing, and it will be SY. These will be true here as well. Just as this was true in the orbital angular momentum case, it will be true for the spin angular momentum case as well. And when you will apply, you had applied L square and you have applied LZ. These were your two operators, if you remember. This was an operator. It was in an eigenfunction in an eigenvalue. LZ was an operator which was giving us the direction along the z component, only one component of it. This is Lx square plus Ly square plus Lz square, and this is the z component of this angular momentum. And there was a specific importance of this one, as you remember, we have studied this one. So similarly, we will do S square and SC as well, as these are also angular momenta. So when S square will apply on a state S and N, we were writing for the L, although we haven't written in this form. This is L, and this will be ML, like the quantum number of the magnetic quantum number of it. And this will be, what was the L square value? H bar, L into L plus 1 H bar, square root in H bar. So H square was L into L plus 1 H bar square. Similarly, this will be H bar square, and this will be S into S plus 1. So the same situation. For L into L plus 1, I am writing S into S plus 1, and the eigenfunction will come like this. This is an operator, this is eigenfunction. This will give this eigenvalue, and then the eigenfunction. And when SZ will operate on this eigenfunction, it will give us MH bar and the eigenfunction. You remember this, we did this for the orbital angular momentum. When L square was operating, for that we were not writing in this form, we were writing like this. L square operates on FLM, right? And LZ operating on FLM. We were writing the eigenfunction in that form. Here we are writing this in the bracket notation. Clear? So, these are actually the eigenfunctions, as these were the eigenfunctions. And similarly, we were having two more operators, L plus and L minus. You remember? These were equal to Lx plus minus IL y. In the same sense, we will have S plus minus as well. And these will be Sx plus minus Is y. And we will have we can apply this on our eigenfunction. S plus minus when operates on an eigenfunction Sm, then this is equal to H bar and S into S plus 1 minus m plus minus 1 and square root, and then we will have the eigenfunction. The eigenfunction S will be there, but m will change, and m will become m plus minus 1. Right? So this one will change when you do a measurement. We know that there are only two possible values, plus half and minus half. The electron is spinning, although we cannot visualize this because it is not physical. But we know that it is having positive angular momentum and negative value of angular momentum. So there are two types of spinning. One is with plus value, the other is with minus value. And when we will do these measurements, L plus, S plus and minus, just like we did L plus and L minus. You know, L plus was the raising operator and L minus was the lowering operator. Here the situation will be not like that. Here they will not be the raising and lowering operators. Why? Because there are no such ladder. There are only two possible values. So either it will make it plus 1 or minus 1. You know that when S is having a value, this one. So you do minus 1 here. What it will be? Minus half. Right? So half is converting into minus half. Similarly, you do the plus 1. So half will be converted into 3 half. But you do that like this. 1 minus half, and what it will be? It will become half. So it will means when electron is, we don't know which of the electron is plus half and which of the electron is minus half. We don't know this fact. But we know that there are two electrons in the S orbit here where I wrote the silver. 5s1. So S1 is having 2 electrons. You know in S orbit there are 2 electrons. So one of the electron is with the plus angular momentum and the other electron will be with the minus. We cannot say that which of the electron is plus half and which of the electron is minus half. We cannot say this thing. It is the same situation like inside a nucleus. You know, inside the nucleus we call the ingredients of this nucleus as nucleons. Why we are not calling them proton and neutron? Like they are proton and neutron inside. But we call them with a combined name nucleon. Because this proton and neutrons are interconverting into each other. The instant it is proton and this is neutron, the next instant this will be proton and this will be neutron. You cannot recognize which one is proton and which one is neutron. You do a measurement and they will interchange. So therefore we give them a name, a combined name like nucleon. So the same story is here as well. We cannot say which of the electron is with plus half and which of the electron is with minus half. You do a measurement on them and they will convert. Like minus half will become plus half and plus half will become minus half. Because the electrons are indistinguishable. You cannot recognize one electron from the other electron. Clear? So you will have to absorb this spin a little bit. It is not something which can be explained very clearly because it is an intrinsic property. So the nature of it we cannot determine, but it is a property that the elementary particles are having. So for today it is sufficient that we got the idea of this spin, that it is an intrinsic property. In tomorrow's class we will do some derivations and then the derivations will make things clear because we will do more mathematics. And this thing came out from pure mathematics, right? And the experiment was there. It wasn't explained with the available mathematics in terms of theta and phi. So spin, the orbital angular momentum is having dependence on theta and phi, you know, spherical harmonics. But the spin angular momentum is not depending on theta and phi. It is an intrinsic property of the elementary particle. Right? Thank you.